In this lecture, we're going to start discussing periodic trends. We are going to look at the sizes of atoms, the sizes of ions, the ionization energy associated with forming cations, the electron affinity associated with forming anions from atoms, and electronegativity, the ability of an atom to pull electrons towards it when participating in a bond. Now, we need to think of some criteria to evaluate these periodic trends. And one of them is electron configurations. As a matter of fact, we spent a significant amount of time working on electron configurations the last 2 weeks. There is a trend in electron configurations known as the Aufbau principle. As you go from left to right across the periodic table, you're adding electrons to atomic orbitals. As you go down the periodic table, you're adding more and more orbitals so that you can add electrons to those. As you go progressively from one element to another, in order of increasing atomic number, you add more electrons and more atomic orbitals. Now, we're going to look at the trends in chemical and physical properties of atoms and ions. These are known as periodic trends, and we're going to look specifically at 5 of them. Atomic radii, that would be the size of an atom. Ionic radii, the sizes of the ions. The ability of an atom to lose an electron to form a cation, that is known as ionization energy. The ability of an atom to gain an electron to form an anion, known as electron affinity, and the ability of an atom to pull electron density towards itself when participating in a bond, known as electronegativity. Now, when we explain periodic trends, there's 4 different ways or 4 different ideas we use to explain them. The first one is electron configuration. The second one is the idea of shielding. And remember that shielding is where the core electrons reduce the attraction between the valence electrons and the nucleus. The idea of effective nuclear charge, which we introduced last time, that is the amount of positive charge felt by an electron in an atom or ion, and a new idea, which is electron-electron repulsions. Electrons in the same group of orbitals repel one another, reducing the pull of the nucleus on the valence electrons. Just to briefly remind you what effective nuclear charge is, it's the amount of positive charge felt by an electron in an atom. Mathematically, it's determined by taking the effective nuclear charge, which is Z star, is calculated by subtracting a shielding constant from the atomic number. And remember that the shielding constant is estimated using Slater's rules. Now, when you look at the periodic table, there is a trend in effective nuclear charge. As you go up the periodic table, it increases, the effective nuclear charge increases. And as you go from left to right across the periodic table, the effective nuclear charge increases. The reason why the effective nuclear charge increases as you go up the periodic table is because as you go up, there are less core electrons, so there's less shielding between the nucleus and the outermost or valence electrons. As you go from left to right across the periodic table, the effective nuclear charge increases. The reason why is because the number of core electrons as you go across a row does not change. The number of protons increases by 1 with each sequential element. If you remember, the contribution to the shielding constant for electrons in the same group is much smaller than if you have groups with n-1 or n-2 principal quantum numbers. So, the effective nuclear charge increases from left to right across the periodic table and from the bottom towards the top. Let's introduce the first of the 5 periodic trends that we will think about today. First is atomic radius. Now, when we think of atoms, we generally think of them as a nucleus with a cloud of electrons around them. I want you to think of atomic size or atomic radius as the volume around the nucleus where 90% of the electrons reside, just like we thought with the boundary surface diagrams that we used to describe the shapes of orbitals. The definition of atomic radius is 1/2 the distance between the 2 nuclei in 2 adjacent atoms in a 3-dimensional framework or in a diatomic molecule. The first part of this definition is shown right here. I am showing a layer of sodium metal atoms. The atomic radius for one sodium metal atom is 1/2 the distance between 2 adjacent nuclei. It's equivalent exactly to the radius, as it is called in periodic trends. In a diatomic molecule like Cl2 gas, the atomic radius is 1/2 the distance between the 2 nuclei in the diatomic molecule. Now, the general trend in atomic radius is that you increase in size as you go down the periodic table, and the radius increases as you go from left to right. So if you start off by looking at the alkali metals, hydrogen is the smallest, lithium's next, sodium is bigger than lithium, potassium is bigger than sodium, rubidium is bigger than potassium, and cesium is bigger than rubidium. So size increases as you go down the periodic table. The reason why is that the shielding increases as you add more and more orbitals. The nucleus cannot pull as effectively on the outer electrons in bigger atoms versus the electrons in smaller atoms. So, since you're adding atomic orbitals and the shielding is greater with more and more core atoms, you expect the atomic radius to increase as you go down the periodic table. As you go from right to left across the periodic table, size also increases, or the atomic radius also increases. The reason why is because there are less protons to pull on the electrons as you go from right to left. So fluorine has 9 protons to pull on its electrons, whereas beryllium has only 4. Since there's less protons to pull on the electrons, the atoms with less protons are generally bigger than those with more protons.